Okay, we are live. Good afternoon, dear Hans-Georg, dear project partners, and all participants. Welcome to our third webinar for the Erasmus Plus project 3D STEAM with the title Accelerating STEAM-related knowledge and skills via 3D modeling and printing. Our speaker today is Hans-Georg Weigand, a senior professor for mathematics education at the University of Würzburg in Germany. He studied mathematics and physics, and he taught at a German grammar school called Gymnasium in German. For many years, he has been interested in the use of digital technologies in mathematics education and teacher education. He has been at various universities in Germany and has twice been a visiting professor at the University of Illinois in the USA. He wrote books about algebra, geometry, and computers in mathematics education. He was the chair of the technology group at CERME in the last few years, and he is the chair of the conference Mathematics Education in the Digital Age. Let's welcome Hans-Georg with his presentation entitled Conic Sections and the 2D 3D Transformation.
Thank you very much, Eve, for this introduction. Yes, you see the title. It's not about 3D printing, but maybe it could be afterwards. We might also think about how to print some conic sections. But I will give an overview. What does it mean? What are conic sections? What is the meaning of conic sections in mathematics education? And especially, I will emphasize this 3D 2D transformation. Let's start with the basics. If you have a cone and you have a plane, and maybe you have a double cone, but what is so interesting about these two simple, maybe three simple objects? If you do the intersection of the plane with the cone, you have three possibilities. You might get an ellipse. A special ellipse is a circle. You might get a parabola or a hyperbola. These are the three conic sections, and we will talk about these and what's the importance of these three curves. Let's start with the questions. What is about conic sections in mathematics education? What is it worth to think about conic sections? And I think they really show mathematics in our environment. They are the basis of applications in the technical world. They show, like the title, the relationship between 3D and 2D geometry, and conic sections can be developed in a new way with digital technologies. Yes, this is so. I will emphasize especially the third and the fourth point, but I will start with the first 2 points, a short overview. Where do we find conic section in our environment? It's a cone, it's an ice cone, an ice cube, and you find it some roofs in this form. You will find it, there is a spinning top, and this is a timer in a conic form, and you might have an ear ring, or you have some kind of road sign in so if you look around in the environment, you find a lot of examples of conics, and or maybe cones, yeah. And if you cut these cones, you have different possibilities. If you do it this way, you will get the same. If you cut a cylinder, and you get, you see it here, and you get an ellipse, and this ellipse you get here with a sausage, yeah, and you get it if you look on the special angle to a coffee or a teacup. You see a table. This is the table of the German government of our Chancellor Merz at the moment. And here you have the oral office, quite well known at the moment. Yes, it's ellipse form. And this is a concert hall in Berlin, also in this ellipse form. And of course, you have the planets around the sun, and the orbits are in conic sections form, especially in ellipse form. And the next one, if you cut it in a special angle so that you have a parallel to the one line of the conic, you get a parabola. You get parabolas on bridges, a lot of bridges. This is the Golden Gate Bridge in San Francisco. You have buildings like this building in Hamburg, or you have the throw of a basketball. It's nearly a parabola, because if there were no air resistance, it would be a parabola. And you have this, is it some kind of a satellite antenna? And the last one, we look for hyperbolas. If you cut it in this way, this is a hyperbola. If you do with a pencil is a cone, and then you have a plane, and this is a conic section. You have conic sections in cooling towers of power stations, and here are two cylindric pipes. If you have the connection between these, you get hyperbolas. And this is a hyperbola, and you have a church in Brasilia, and you have some roof. And the special thing is that you have straight lines. You can build these roofs out of straight lines. This is the reason why they're quite stable. And you build these roofs here. We come back to this later. No, a lot of conic sections, wherever you look around in the environment, you find the conic sections. What is about conic sections in mathematics classrooms nowadays? Yeah, if we look back to the 18th and 19th century, conic sections were compulsory content in geometry in many countries, in Germany, France, Italy, and some others. And especially if we see Felix Klein, he has done the big mathematician, German mathematician. He has done the Murano resolution, and since then, since 1905, calculus comes into German classrooms. I'm not quite sure how it's in other countries, but in 1905, he wrote that conic sections are the organic connection of elementary geometry, descriptive geometry, analytic geometry, calculus, differential geometry, and projective geometry. So conic sections do the connections between these different fields of mathematics. And he thought, yes, it's very important. You have to do conic sections in mathematics classrooms. And then in 1950, 1970, 80, conic sections were a regular content in analytic geometry in Germany, maybe also in some other countries. I'm not quite sure. And if we look at a textbook from 1970 and 1980, it's in German, but you see that there are conic sections really done in a quite complex way. Yes, we come back to some of these pictures later, but then since 1980, the stochastics displaced the conic section because there was a new topic in mathematics education, stochastics, and though you had to cancel some other subjects. It's quite difficult to cancel subjects in calculus, and so the geometry was canceled, and especially the conic sections weren't taught since then in German Gymnasium, in the German grammar schools. And if we look at the mathematics classroom nowadays, where do you find conic sections? Of course, as graphs of a quadratic function, parabolas. Then you find them in a hyperbola, in an anti-proportional function, also a graph. You find ellipses if you draw, yes, these solids in 2 dimensions, then the circle comes to an ellipse, and circle is, of course, a special ellipse, but not more. In common schools in Germany, this is what you do in conic sections, and we will think about how it might be possible to find possibilities to integrate conic sections a little bit more into mathematics lessons. And because conic sections, you've already seen it if you look back in mathematics education, conic sections an important topic in the history of mathematics, and so we can learn something from this history, and so we do a short look back in the history and of conic sections. When did they appear the first time? Maybe it was around 400, 300 before Christ, and it was the problem of doubling the volume of a cube, and it is a well-known topic. Yes, if you have a cube and you want the side of a cube which has double the volume of the original cube, you get this equation. And Menaechmus was the first who tried to solve this problem, and he has done it like with 2 geometric means. So if you have a and 2a, yes, and you want to calculate the new side of this cube with double the volume, he has done these 2 geometric means. It's a to x, like x to 2a, and the same here, and here is x to y, like y to 2a. This was the idea of Menaechmus, and if you do this, you come to these equations, and you see this is a hyperbola, and this is parabola. Of course, Menaechmus haven't had these formulas because the formulas weren't known at these times. They had to do it in a geometric way, and so he tried to get a solution on a graphical level, and maybe he was the first that he thought about the intersection of a parabola and a hyperbola. And it's not quite sure whether he already had known that this is really an intersection between a plane and a cone, but these concepts appeared the first time in history in mathematics. And then Euclid, Archimedes, Apollonius, they already knew a lot about conic sections. They found all the properties. We knew until the 17th, 18th century, the whole properties of the conic sections were already developed or found in these old times in the Greek mathematics. And Apollonius, he wrote a special book on conic sections. So they really knew a lot about conic sections. And then coming to then nearly the medieval times, or the starting of the new time, when here was the painters like here Albrecht Dürer, and what they looked for was to how to draw the pictures in 2 dimensions, so you get the transformation from 3D to 2D, and this was a quite interesting method to do it, because you have this plane, and this is a straight line, and you always find the points of this object here in 2D. And so they were interested in this. They wanted, and they were the first who thought about the central perspective. So I will a few words about the central perspective. Another one, so Raphael, who has done this famous painting School of Athens. This is already painted, you find this painting in Rome, the Vatican. Here is the original painting where he has done it. And you see, this is the central perspective, and you have this vanishing point here in the middle of this painting. And this is what these painters in these times developed the idea how to paint realistic pictures of 3D situations. And it's the same with Leonardo da Vinci. Here is also this painting is done in a central perspective. It's not quite right. This is because the length of these windows, if they should have all the same length, then it's not well done in the perspective way. So these windows should be a little bit shorter. So it's not known whether Leonardo has known this, or maybe it was the beginning of the painting with the central perspective. So, and all the properties were not really known. And it's the same here in this Raphael painting. This line here of this arc is too long compared to this, if these had the same length in reality. So there are still some faults or mistakes in this sense concerning the central perspective. And now Dürer, he wants to know, if you do an intersection of a cone with a plane, what is the real size of this intersection? So he asked this question, and he has done, this is the original painting of Dürer, and he has done it quite thoroughly. And then he got the result. The intersection of a plane with a cone is an egg line, because it looks quite similar to the shadow of an egg. So Dürer did not know what the Greeks already found out. So he did not know these writings of the Greeks. He has done it by his own, and this was his result. And if you see it, if you compare the ellipse with an egg, then here the egg here is a little bit smaller, so it's not an ellipse, it's something different. And this is also, if you cut a cone with a plane, it seems to be intuitively that here the curve is smaller than here. And that this is not the case is in some kind surprising, yes. And you have to draw these real size of these intersection points very thoroughly to get the result. Of course, nowadays we can do this with digital technologies. And if we do the same construction than Dürer, hopefully now you should see now the GeoGebra 3D simulation. It is the same what Dürer has done, of course, without technology. And if this is the plane, the plane. Here you see the intersection points, and this construction, which I don't know explain in details now, is you can do this in the real size you get here. This is the intersection in the real size, and if you do it a little bit more thoroughly, and I can. So, and this is, and then you see it's an ellipse. It's not an line like Dürer thought. So, but this is the construction. It's exactly the same construction like Dürer has done it. You do this in maybe you can do it in geometry, and with digital technology, it's more easier to do it than doing all these things by hand. So, though this is the ellipse, maybe I am not quite sure whether I should explain what really an ellipse is, but maybe we might have a short look at it. You have 2 points, and you have this point, and the sum of the distance from F1 to P plus P to F2 is constant. It's always the same. And if you do this, then you get at the end an ellipse here. An ellipse, this is the construction of ellipse. So this is the definition of an ellipse, that the sum of these 2 straight lines of these 2 distances is always constant. Can show in this ellipse, and we come to this later. So, and since in the 17th century, ellipse got a very important meaning because Galilei and Kepler, they found out that the planets move on ellipse around the sun, and then Kepler's law come out of this, and so conic section, especially ellipse, got a very important meaning at these times, and now these mathematicians studied the conic section, and they also found what the Greeks already found out about all the properties of the conic sections. And René Descartes in the 17th century, when he has done the relationship between algebra and geometry, or maybe geometry first and algebra, he found the analytic geometry, and he proved his method with the formulas in algebra and the analytic formulas with conic sections. So this is an original painting of Descartes, and he has done this special construction of an ellipse, and maybe I show you an example how you can do it nowadays. It's a nice construction, and I will show it to you, and maybe you know this guy if you know now Matthias Ludwig from Frankfurt. This was a few years ago, yes, when we worked together in Würzburg. Matthias Ludwig comes from Würzburg, and we've done this video some times ago, and it's an easy method, yes, to draw an ellipse. So, and this is exactly what we have done with GeoGebra. You can do it here, maybe in a more nicer way. And if you take another length, and then you can do 2 ellipse, and they have the same foci, focus 1 and focus 2. These are these 2 points. Yeah, this is, so Fine. So and if you go to Gießen, in Gießen is a mathematics museum. I think it's the only museum in the world only for mathematics of Professor Beutelsbacher. Then he also has done this construction. It's exactly the same construction of an ellipse. This is I only give the equation of an ellipse here. You see it. If you have A equals B, then you have a circle. Otherwise, you have this ellipse with these two distances A and B here. We come back to this. And if we go a little bit further in history, it was an important point when Dandelin discovered that you get the foci of an ellipse and also of the conic sections if you take the cone and you do two spheres into this cone, and they intersect the cone here, especially around this circle. This is a model here of this, and of course we can do now a simulation, a digital simulation of this Dandelin spheres, and here you have these are the two spheres with a plane, and these spheres here, exactly here, they intersect with a cone, and this is the plane. And if you can change the angle of the plane, and then you get different here ellipses. We stay with the ellipses. We will go on to the parabola and hyperbola later. But what does this show here? The main point is that here is these 2 points, F1 and F2, F1 and F2. These are the points where the spheres here intersect with a plane. And if you look at this point, this is a point on the ellipse. And so this line and this line are tangent lines to the sphere. And so they have the same length. So F2 to this point here is the same than this distance. And it's the same for the other point. And so you see, because this green line is always the same if you go around here with a point on the ellipse. And so you see that F1 x plus x F2 is always constant. It's not, you have to see it in a little bit longer. Maybe it's a little bit clearer here that you see here is the point F2, here F1, and you have these two lines F2x and x to this point G and x to H and x to F1, and this makes that it's always the same length like this one, and you get exactly that this is the definition of the ellipse, and you get this definition out of this idea with the Dandelin spheres. And so this is one of the relationships that you have 3D 3D objects, and you go over to a 2D object, but you explain it in the 3D simulation, and you get this curve in the plane, you get an ellipse. And this is the same also, it's an experiment in the Mathematicum. It's this museum in Gießen. You have the cone, and you can, this is a liquid inside the cone, and you can change the angle of this cone, and you get the different kinds of conic sections. You get ellipses, parabolas, and hyperbolas. And coming to the definition of the parabola, maybe I do because in nowadays in school, parabolas are only known as graphs of quadratic functions, but in a geometric way, parabolas are defined in another way. They defined if you have a straight line and you have a point F, and then you do you look for a point which has the same the same distance from F and to H, so the same distance to this point and the straight line. So P here, and you see that here are these two lines are have the same length. And so, and this is the definition of a parabola, that all points which have the same distance from a point and a straight line is a parabola. And you can see it here. If you do it, you get exactly the parabola. Yeah, this is the geometric definition of a parabola. This, and if we transfer it to algebra, you can show, yes, that you can calculate, but I don't do it now here in details. If you do this Pythagorean theorem, and then you get that if you have this condition that P has the same distance from F to H, then you get the formula of a parabola. And so this is exactly the other way around. Usually in mathematics, you have this this quadratic equation and you draw the parabola, and this is the other way around. You have the definition of the parabola that we just seen it, and you get the quadratic function. Yeah, and you can also see this definition of a parabola with Dandelin spheres, but this is not so easy to explain and to see it. You see it on this quite complex picture that you have to do some additional lines to see this relationship. And but it is, you can do it. You have here the parabola, and you see this straight line, and you have the point here, and you have to show that this point X has the same distance from F1 to L. You can do it, but now it's we don't do it. Maybe I have done a simulation in GeoGebra, but even it's not so. It's easy to see that this plane is parallel to the side of this side of the cone, and you only have one sphere, and then you can show that this is a parabola. We don't want to do this in details now, but it's again an example of the 3D 2D transformation or relationship. And another example of this relationship is if you do a function or the graph of the function of two variables, and this is maybe one of the easiest functions, as f of xy is equal x times y. And if you can do also this graph with the 3D mode of GeoGebra, and you get exactly this. This is the graph of this function, you especially see the straight lines. And if you have x times y, if you have x constant, then you have a straight line in y. And if y is constant, then you have z equals x times a constant, then you have also a constant. You see that this is done, or these straight lines are part of the graph of this function. And if you have especially this, the plane x equals y, so if x equals y, and you think of the function f of x is x times y, if you have x equal y, then you have the a function and the graph of the intersection between this plane and the graph of this function is a parabola, because it's x squared or y squared. Yeah, it's in two ways here. You have, so you can see some conic section, especially this conic section here of the parabola in the 3D graph of this function. Here I have again a picture of it, and you have this plane is x equals y, and the intersection of this plane with the graph of this function is a parabola. It's a parabola, and coming to the hyperbola, and we could go now, if you were in Würzburg, there is a museum in Würzburg. It's a museum for geometric arts called Kulturspeicher. And in this museum, you find pictures of geometric art. And here are some pictures of this geometric art. And we are interested especially in one picture, and this is one picture here in this museum. And maybe you already recognize that this is a part of this graph of this function x times y. And this was the idea of this artist to do this the surface in this way, and he was quite proud of his work. And this is the artist, the left one, yeah, not the right one, yeah, the right one. It's some years ago, and this is a quite creative artist. Yes, this was his next work, nearly the same, a little bit different. And this was his next work. It's nearly all, he always has done the same work and with a little bit of variations, but it's anyway, it looks fine. So if you stand in front of this picture here, it's really impressive, because you have the impression that it is a 3D picture, but in reality it's really only 2D. Yeah. So this is the another example of this relationship between 2D and 3D. If we look at a parabola in 2D. Now, this simulation is done by my friend Jürgen Elchenbroch, and he has done this parabola, and you can rotate this around the y-axis. So you can rotate this around the y-axis, and if you do the surface of this rotation, then you get this in 3D. Yes, and this was what we have already seen as the satellite antenna with special properties, why you can use it as an antenna. This is a different aspect you can of course, see it. So again, the relationship between 2D and 3D, and you can also do this with this is again the picture with the parabola. This is yes, this is also in the museum in Gießen. If you rotate this is a liquid, and if you rotate here, there is a cylinder, or this special piece of this cylinder. If you rotate it, then you see here the liquid builds parabola. There is the relationship to STEM, to physics, why this is a parabola. Yeah? And we do the same what we have done with the parabola. We can do it with an ellipse. And an ellipse here, again, this simulation of Jürgen Elchenbroch, and now we can write the equation of an ellipse. This is x squared. No, going back to. Oh, I have to go back here. Is it x squared, hopefully, or is it again? I will go back. I will start it in a new way. Let's do it here. So now I will write here in let's do it in this way. X squared divided by, say, 16 plus y squared divided by 9, and this is equals 1. Then you get this ellipse, and we can rotate this ellipse around the x-axis. And again, we can see the surface of this solid, and we get an ellipsoid here. Yeah? An ellipsoid. Yeah, this is an ellipsoid. And again, an example of this 2D, 3D relationship. And you find some objects in the environment which are nearly, it's not a real ellipsoid, it's only nearly. Also this one, or this one, or this one, or this one. So you have examples of this ellipsoid, nearly ellipsoids, in the environment here. So it would be the next step to calculate the volume, for example, of the ellipsoid, and to get the volume of these objects, which would be a possibility for mathematics education. So now I have some special problems. You see, now we have 45 minutes, so I think I can do some of these examples. And maybe I explain first, where does the name parabola come from? Why is it called parabola? We go into this. So where does the name parabola come from? And the name is, if you do a construction, and you want to have a square which has the same content, the same area than this rectangle. Here's a rectangle, and you want a square with the same area. This is it's a well-known construction. You do here the point C, and you have the circle of in Germany we call it circle of Thales. Then you get here a right angle triangle and you get this square. And you know that this square, yes, has the same area than this rectangle with these sides. So, but what has this to do with the parabola? If you change this rectangle, the side of the rectangle, and you see the locus of this point G, then you see if you have here the locus of this point C, and you see that it is a parabola. So if you have this parabola and you have the point D, you immediately get the length of the side of the square, which has the same area than this rectangle. And this is the name. Parabola means it's the same becoming the same, and this is the name. Maybe the Greek used this name because it's the same concerning the area of this rectangle and this square, and they got this line and called it parabola. We have parabolas also in parabolas. In German, it's Parabel in the literature of Lessing. Yes, I only know the name in German, Nathan der Weise. I'm not quite sure what it is in English called. And then you have the ring parabola. And so it's still a word also used in other sciences. So this is the parabola the name comes from. And what do I have? Another example is the man or the woman on the ladder. And this is a construction here. If you have this man or woman is going up and down this ladder, yes, and you know that this is dangerous because this ladder can slip away. Yeah? And if the ladder slips away, the question is, on what locus moves this point F if the point A slips away or moves along this x-axis. So if I move this, so what is the curve, the locus of this point if I do this? You can, if you don't know this problem, you can think about just how it is here. It is easy to do it if we do the locus here, and you see it's here, and it is done in this way. So I think you recognize it's really not what you might thought. I also thought it in a different way when I've heard the problem the first time, but it's an ellipse. It's an ellipse. And especially this way of drawing, this is a quite interesting idea for an instrument of drawing ellipses to move around this straight line here, and you can of course take a different place of this point and you get different ellipses. Yeah. It's quite interesting. I think I see it as an interesting problem. Yeah. So this is the man on the ladder. The relationship between ellipse and a circle, we already talked about this. What is the relationship if you have the equation of a circle? Here it's with the radius 5. And then you take any point A here any point A on the x-axis, and this M is the midpoint of this distance AB, and the midpoint. And if you say this is AB is y and AM is y prime, then you get y prime is the half of y, of course. Y prime is the half of the distance AB of y, and they get y prime is the half of y. And then you have this equation if you say x and x prime is the same, it doesn't change, but y is changing. If you say y equals 2y prime, then you get this equation, and you get x prime squared plus this times 1/4 is 5 squared, and you get this equation, and finally you get this equation, x squared divided by 5 square plus 5, you get the equation of an ellipse. You get this is the equation of an ellipse. So if you do this transformation from a circle, you get the ellipse, and this shows the relationship between these two objects, between a circle and an ellipse. And in a general way, the equation of an ellipse is this, what's written here, with these two length A and B. And if A equals B, of course, then it's a circle. So this is the relationship between these two. And what else do I have? Last one, the area of an ellipse. This also gives us the area of an ellipse. If you have a circle and the area of a circle, it's A squared times P. And if you think that all these very, very small, nearly rectangles, they are divided by 2, or there is a transformation. Maybe it's not only the midpoint, but you get this y prime equals b divided by a times y. So we just used it with b to a equals 1/2, but you can do it in a general way, and do it with these nearly rectangle to this rectangle, then you get the area is divided by this factor b divided by a, and finally you get the area of an ellipse like this one. Of course, this is only done on an intuitive level and not on a real mathematical level. This you had to do with calculus, of course. But this is, it shows that there is a narrow relationship between the area of a circle and the area of an ellipse. So these are the problems. We come to the end. And I think, and hopefully I've shown it, that conic sections are interesting objects in our environment, that they show the relationship between 3D and 2D, that they can show some highlights from mathematics history, because they are very important objects in mathematics history. And like the last one, they are a source of interesting geometrical problems, and a lot of problems coming out from conic sections if you do it, and especially if you do it in an analytic way, like in analytic geometry, you get a lot of geometrical problems you can solve on a geometrical level, but also on an analytical level with formulas. So this was my talk. Thank you very much. And I go back to Eve, and if you have any questions, feel free to ask it, or any remarks, or whatever you think, you can say it now. Eve.
Thank you very much, Hans-Georg. It was a very interesting talk. And of course, we agree that conic sections are interesting, that they show the relation between 2D and 3D, that they are interesting source of interesting geometric problems. Yeah, you already pointed it out. If our viewers on YouTube have questions, feel free to write them in the chat and I will forward them to
Yes,
Hans-Georg.
fine.
Yes, there's a first one. So the question is the tendency in Germany similar to other countries where geometry gets less and less attention in the curriculum? I'm thinking about secondary education. What do you think about it?
Yeah, it is a problem in Germany. As I already told that stochastics, probability theory, statistics, getting, of course, it is important, and you have to do it on secondary level, lower secondary level, and higher secondary level, and then you have to cancel other subjects, and it is not so easy to cancel contents in algebra. So it was also in Germany that the geometry, a lot of interesting topics in geometry were cancelled in secondary, in lower secondary school, but also in analytic geometry. And this is especially done that geometry is getting more and more on an intuitive level and not on a quasi-axiomatic level, that you do less constructions with circle and ruler, that geometry is more concentrated on the calculation of areas and volumes. And these what I think the fantastic, the wonderful construction geometry, that really this is true. Yes, it's getting less and less, and this is, yes, it's a sad thing, but if you do it, you have to spend some time on it. And of course, we agree that it would be important to do it. It would be fine to do it. It shows very special properties of mathematics. But yes, it is true. It's getting less in it, but it's difficult in Germany because we have these 16 states and every state is different. So yes, in some states it's getting even more or less. In other states, Bavaria, it's still existing, but it's not. I think it could be improved, and there could be some more of geometry. Yes, I agree. I cannot hear you.
True. I muted myself not
Yeah.
to interrupt your answer. Thank you very much for your answer. Hopefully the question has been fully answered. If not, re-ask or reformulate.
Yeah, you can also say it how it is in some other countries. In my opinion, if we go to France and Italy, there might be still might be some more geometry and more emphasis on this construction geometry than in some other countries, saying in the northern part of Europe, England, and maybe also Germany. It's my impression. But maybe it's only true for some special schools.
So we got the confirmation that you fully answered his questions and he thanks you for it. Are there further questions? If not, we stop streaming. Last call. Okay, so ich habe den Stream jetzt beendet.
Okay. Da können wir wieder zum